Hello, my name is Abigail Northrup, and welcome to my video describing my 2020 research combining signals of dissolved oxygen and carbon dioxide to infer whole strain metabolism. This PowerPoint will provide context to my research poster and a summary of the methods and conclusion. Metabolism is energy that is being stored and moved through an ecosystem in various forms of carbon. A few variables help to measure this carbon in the system. The first is ecosystem respiration, ER, representing the total respiration of organic carbon to CO2, carbon dioxide, and the second variable, gross primary production, GPP, represents the ecosystem's ability to transform solar energy into biomass by photosynthetic processes. These variables drive metabolite gas levels, including dissolved oxygen, DO, and dissolved inorganic carbon, DIC. GPP and ER work inversely of one another on the metabolite gases. By measuring metabolite gases, we can infer the productivity of the system. However, metabolite gases are also affected by gas exchange and day and night cycles. The day and night cycles drive photosynthetic processes and consequently DO and DIC levels, while gas exchange tries to create an equilibrium of gas concentrations between the terrestrial and aquatic environments. Metabolism estimations are used to determine if an ecosystem is net autotrophic, a system that is building organic carbon into biomass, or net heterotrophic, a system in which more organic carbon is being respired than biomass produced. Stream metabolism estimates have traditionally used collected dissolved oxygen data in a metabolism model. Recently, the ability to automatically measure dissolved inorganic carbon as carbon dioxide gas has become another method to infer stream metabolism, also providing insight to the metabolic and physical processes of the stream. Due to the inverse nature of DO and DIC, we anticipated the metabolism estimates to be the same, but they are variable. The purpose of this research is to gain a better understanding of what could be the cause. We performed sensitivity analyses of model variables among two different models, one that infers from DO data and the other that infers from DIC data. The four variables tested include GPP, ER, K600, that is a calculated gas exchange, and the photosynthetic quotient, PQ, that is a stoichiometric control on oxygen released to carbon fixed. Baseline values for the sensitivity analysis were collected using a literature review and an optimization exercise in the DO and DIC models with observed metabolite gas data. The collected baseline values for the variables were then inputted to the DO and DIC models and varied in increments to study the change on the metabolite gases. These outputs were overlaid on the observed metabolite gas data to determine the accuracy of the changed variable. The sensitivity analysis of the gas exchange variable K600 shown here shows the inaccuracy between the observed data being the hollow black lines and the model's output being the colored gradient. The rate of change graphs on the top row show where the model output had the largest margin of error relative to the observed data. Similar results among the other variables were observed. The sensitivity analyses of the model parameters helped our understanding of the differences between the DO and DIC models. We learned changing an individual parameter will not create a more accurate output relative to the observed data. The sensitivity analysis provided a segue for this year's research that focuses on the metabolic stoichiometry of GPP and ER. With this research and subsequent building blocks, I am hopeful the cause of the discrepancy between the DO and DIC models will be identified to provide an accurate depiction of stream metabolism. Accurate measurements create the potential to use metabolism as a monitoring means. For example, this tool could better understand the ecological response to the recent floodplain restoration of the Upper Clark Fork River in Montana and future ecological and anthropogenic impacts. Thank you for viewing my PowerPoint.